And welcome back. In this lesson we're going to talk about section 4.1, the beginning of chapter 4. In chapter 2 we introduced functions and talked about the different properties of functions. In chapter 3 we introduced two types of functions and studied them, polynomial functions and rational functions. Well, in this last unit, Chapter 4 and parts of Chapter 5. In Chapter 4 we're going to introduce two more types of functions and study them. They're exponential and logarithmic functions. These functions are a bit different than your typical ones we've looked at before. These types of functions are called transcendental functions because their description transcends algebraic description. It isn't just multiplication, division, addition, and subtraction that produces them. There's some more complicated operations because the only thing that defines a function is that each input only corresponds to one output. Beyond that, you could have any mechanism that produces a function. That's why some functions have very complicated definitions. One course that is basically a study of a small set of functions is trigonometry. It's basically just a study of a small set of functions. And the first part of the course really is just defining how the functions work. So, we're going to talk about exponential functions today. So let's bring that up. Now, exponential functions are transcendental functions. Transcendental. If you want to know how to write that word, it's our first. Transcendental. Transcendental function. So exponential functions are our first transcendental function, and they're kind of baby's first transcendental function in that they're not very transcendental. I don't think you'll really have any trouble understanding where we get them. Their inverses will be more of a problem. But we'll get to that when we get to that. The exponential function with base a is defined for all real numbers x by f of x equal a to the x, where a greater than 0, a not equal 1. So a simple example would be 2 to the x, or 1/3 to the x, or 3 to the negative x, or 5 to the 2x minus 1 plus 1. That is a exponential function that has been shifted both horizontally and vertically, and also I believe that would be a horizontal shrinking. It has to delve back in my mind to section 2.5, but yes, I believe that would be a horizontal shrink. So, really the new thing we're doing, the new operation we're doing in these functions is we're putting the variable in the exponent. Now, why do we make these conditions on the base? Well, really it's to avoid ambiguity. If you think about, say, if I had 0 to the x, well, that wouldn't be a very interesting function because 0 to any positive power would be 0, just 0. And if you had 0 to a negative power, like negative 1, that would actually be undefined. So, we avoid that. We also avoid 1, because what's 1 to any power? Well, 1. And y equals 1 is not really a new type of function, it's just the horizontal line, y equals 1. Why not negative? Well, you get into troubles about what if you're considering something like this. Negative 2 to the square root of 2. Well, we know how to deal with fractional powers or finite decimals because we can just convert them to fractions. Because you may remember from way back in chapter P that if you had like negative 2 to the 2/3, well, that is the cube root of 2 of negative 2 squared. That's easy enough to deal with. But what about something like this? You can't write this as a fraction. How do you even know what sign it's going to have if you have an infinite non-repeating decimal? Well, we don't. So we just ignore it. So our bases are only going to be positive and not equal 1. Okay. Let's actually look at one of these functions. So let's graph 2 to the x. And yeah, I'll do it by hand first, then we'll look at it in the calculator. Let's make a point table for f of x equal 2 to the x. This will be some good review for you in some exponential math. So 2 to the 0. Anything to the 0 power? Well, if you don't remember, 2 to the 3rd is 8. 2 to the 2 is 4. 2 to the 1 is also basically building my table. Is 2. How do you get from one power to the previous? Well, 8 to 4 you divide by 2. 4 to 2 you divide by 2. Yeah, you get from a power to the previous power by just dividing at the base. So 2 to the 3rd divided by 2 is 2 squared. Divided by 2 is 2 to the 1. So 2 to the 0 is 1. So 0, 1. And then as we saw, 1, 2, 3, 8. Skip 1. 2, 4. How about if we go negatives? Well, that would be 2 to the negative 1, which, if you don't remember, would be 1 over 2. Get the same thing by following this progression. Keep dividing by the base. 1 over 2. Divide by the base again, you get 1 over 2 squared, or 1 over 4. So negative 2 would be 1 over 4. Alright, that's plenty. I actually don't need... Oh, bother. There we go. This is what I want. I actually don't need really any negative y space. So I will draw my x-axis down here. And honestly, I'll just go by these things. This will be good enough. So, at 0, it is 1. At 1, it is 2. At 2, it is 4. At 3, it is 8. At negative 1 is 1/2. 1/4. And we could keep going 1/8. But you can see as it keeps going over this side, it's just getting smaller and smaller. Whereas on this side, it's going up to infinity. I can plug in any x, so the domain, and this is going to be true for all basic exponential functions, domain is always going to be negative infinity to infinity, or all real numbers. The range is more limited. You can see here, no matter what negative exponent I put in, I'm still going to get a positive number, because 2 to the negative 20 would be 1 over 2 to the 20th, which would still be a positive number. So no matter how far I go left, it's still going to be positive. It's just going to be small. So I'll have a horizontal asymptote at x-axis. 0. Oh, messed up my parentheses there. And that's horizontal with a period to indicate a abbreviation. And horizontal asymptote at x-axis. What else? Oh, range. Range. It starts at 0 and goes to infinity. Oh, actually, should be a parentheses there, because it does not touch 0. There we go. 0 to infinity. And obviously, if you did a shift of this function, like f of x equal to the x. Alright, so let's do a different color. Do f of x equal 2 to the x plus 2. Well, then, of course, it would have been shifted up. I graphed it a little bit off. It would have been actually more up here. But you get the idea. It's just the same function, just shifted up by 2. And, you know, if I did 2 to the x minus 2, it would be shifted down. And you can still do horizontal shifts as well. 2 to the x minus 2 would be shifted to the right. Let's see here. And 2 to the x minus 2 would just be shifted to the right. So it would have basically had its crossing point here. And I screwed up. Oh yeah, that's not a very great graph, but you get the idea. Just be shifted to the right one. So it'd be crossing there, be 2 right here, and be 4 right here. Alright, I wasn't that far off. Yeah, not too bad. Okay. But yeah. Exponential functions will all look basically like this. The only difference from this and, say, grab another one. If I had g of x equal 3 to the x, is still have this point, but then it would go up more quickly, because 3 to the 1 is 3, and 3 to the 2 is 9. And then it'd also go down more quickly, because 3 to the negative 1 is 1/3, 1/9, 1/27, etc. So the only difference between graphing 2 to the x, 3 to the x, 4 to the x, 5 to the x is it will be a steeper turn at 1. At 0, I should say. Become a sharper and sharper curve. Okay. That's what basic exponential functions look like. What kinds of applications are there for exponential functions? Well, the truth is there are a myriad of them because many, many things change exponentially. A quantity that changes exponentially instead of just adding on again and again, like I get $2, then I get $2, then I get $2, then I get $2. Something that changes exponentially is something that multiplies. So I have $2, then I get multiplied by 2, I got $4. Get multiplied by 2, have $8. Multiplied by 2, get 16. Multiplied by 2, have 32. Multiplied by 2. It increases much more quickly than just an addition, because it doubles or triples each time the operation happens. So a lot of things change exponentially, but probably the most common is interest. Interest is calculated using exponential functions, or compound interest is. And the idea with compound interest is that you have an amount in the account, and say you get interest based on the amount you put in the account, but also on the interest that's already been added. So, for example, I have a savings account that's compounded quarterly. So, how that works is you take your basic interest rate, like say I had a 12% interest rate, and I get interest 4 times a year, every quarter, so every 3 months. So the way it works is I get 3% every 3 months. Now you might say, well, how's that going to be any different than getting 12% at the end? Well, it wouldn't be any different if it were just 3% of the initial money I put in the account. But it's 3% of whatever's in the account at that time. So say I actually started this in January. So January to March, this is the first quarter. I would get 3% of whatever was in the account at the beginning. So let's say I had $100. I get 3%, that would be $3. So I'd have 103 in the account. Go to the 6th month, that would be June. You'd get another 3%, but this would be of everything in the account. So I get 3% of the 100, but also 3% of the $3. So you get, let's see, $3 and about $3.03, I think. And similarly, the next, let's see, the 9th month, I believe that'd be September. Next 3 months, you get 3% of everything that's in the account. And then December, at the very end, you get 3% of everything that's in the account again. So you'd end up with more, not necessarily a whole lot more percentage-wise, but more than you would get from just getting a base 12% of whatever you started with. Because it continually counts how much you had in the account before it calculates interest. So here's the formula for calculating that. You take the principal, which is the original amount, times 1 plus r over n, where r is the interest rate, n is the number of times the interest is compounded per year. So for the example I gave you, I had $100 compounded at 12% quarterly, so n would be 4. And then up here, 4 times the number of years. So let's actually do the problem I just made up. So if I had $100 at 1 plus 12%, so 0.12 over 4 to the 4, and let's just do a single year. That would be 100 times 1, let's see, divided by 4, that'd be 0.03. So 1.03 to the 4th. And let's compare that with what I get from just adding 12% at the end of the year. Well, I know what that would be. I'd get 112. But it would be 100 times 1.12 would be how you calculate it. But yeah, I have 112 at the end of the year with just simple interest. So if we do 100 times, what was it? 1.03 to the 4th, we'll have 112 and 55 cents, which is more money. 112 and 55 cents. Not necessarily a lot more money, but percentage-wise, you know, if this were instead of $100, say it were $1 million, you just move the decimal point 4 places over, and you're dealing with like, see, that would be a $5,500 difference, which might make more of a change to you. So, and as it'll be a larger difference as time goes on. So I mean, as you go out to 10 years or 20 years or 30 years, it'll be a bigger and bigger difference. Let's do some examples. Oh, while I'm thinking about it, might as well point out it's not difficult at all to plug in these things. If you want to, say, do 3 to the x, just do 3 to the x, or 4 to the x. Just don't forget, if you're going to do something in the exponent, like 5 to the x minus 1, don't forget you'll have to put it in exponents. Or you guys probably have math print, so you can, it'll actually shift it up there for you, so that'll work just fine. There's 3 to the x. There's 4 to the x. Oh, must have been the other way around. Yeah, 3 to the x is the 1. Oh, no, that's right. 3 to the x. I forgot, I shifted 5 to the x over. 1 unit over, that's why it's over there. It is going up more swiftly than the other two, though. If you take away the minus 1, you can see that. I thought we might look at this problem 48 here. A certain breed of mouse was introduced onto a small island with an initial population of 320 mice. And scientists estimate that the mouse population is doubling every year. Find a function that models the number of mice after t years. Later on, I believe in the last section of this chapter, we'll get a standard exponential growth or change function. And you can actually look ahead in the book if you really want to find that. But it's not too hard to come up with this. If you know that the mouse population doubles every year, well, you can start off by saying, okay, whatever our initial population is, it's going to get multiplied by 2 for every year we have it. So, it's like, we have a to the x. Well, in this case, it's going to be 2. Because, or in this case, I guess I'll say, they want me to use the variable t. So I'll say t. Yeah. I'll redraw it. Probably change my color of this marker here. Let's go back to blue. I like blue. 2 to the t. And that's not perfect though, because at times 0 we'd have 1. And we don't have 1 mouse, we have 320. Why you just say, okay, 1 times 320 would be the correct function. So the function that models the number of mice after t years would be f of t equals 320 times 2 to the t. Estimate the mouse population after 8 years. Nothing is easier. Just calculate for 8. 320 times 2 to the 8th. That should be quite large. Exponential functions increase very quickly. So, 320 times 2 to the 8th. 81,920 mice. And just think about how fast that would go if it kept doubling and doubling and doubling. That's why pests can be a very large problem, because living things tend to multiply exponentially if there is sufficient resources for them. Let's do an interest problem. Let's do 55 here. Find the present value of 10,000 if interest is paid at a rate of 9% per year, compounded semi-annually for 3 years. So semi-annually would be twice a year. So that would be, let's see here, our new amount would equal, our principal was 10,000, so remember it was P times 1 plus R over N to the NT. So 10,000, I missed a 0, times 1 plus, let's see, 9%. So always write it as a decimal, so 0.09. Twice a year would be semi-annually. Over 2 to the 2 times 3. So that should be 10,000. Let's see, 0.09 over 2 is 0.045, so that'd be 1.045. You don't have to do this step. I often do it just to make my calculator work a little bit quicker. But it's fine to just plug this in as it sits. Just remember to put, well, it won't matter to you. Never mind. 1.045 to the 16th. Well, let's go with that. 10,000 times 1.045 to the 16th. Just using my numpad here is how I get it to go without actually clicking, but I mean it would be 10,000 times 1.045 to the 16th. So 20,223 and 70 cents. Usually rounded off at hundredths because that's where our money system rounds off. So 20,223.70. And we're good. That should finish us off on 4.1. Next time, we'll have a very short section. 4.2 is about a specific exponential function and how it's found. I'll talk to you then.